Hello, and welcome back to Algebra 2 Notes with Miss Faust. Today we are moving on from solving rational expressions to using rational expressions and equations for application problems. The two most common kinds of problems you'll see with this are distance, rate, and time problems, and then work problems. And we'll do a couple examples of both so that you have an idea. What you'll see is that the challenging part of this is setting up the equations. Once you get the hang of that, it's using all those strategies we've been using to solve problems to find your answers. So just a little introduction. Rational expressions and rational equations can be useful tools for representing real-life situations and for finding answers to real problems. Think back to Justin's t-shirt business at the beginning of class, or at the beginning of the unit. That was that type of problem. In particular, they're just useful for describing distance, speed, time questions and modeling multi-person work problems. We're going to do distance, rate, and time problems first. So what we're talking about here is we're talking about cars going and coming, or bikes, or people walking, or trains, anything like that. So we use the formula distance equals rate times time, where d represents distance traveled, t represents time, and r represents the speed or rate. So in most problems, it's going to be this t equals d over r that we're going to be working with primarily, because we're going to know something about times, or we're going to be looking for something about times. So time equals distance over rate is the most useful one you'll find as we go through these. So in example 1, we have Sally driving to Daytona Beach, Florida, and then driving back again. So we're going to say that she had to drive 1,500 miles to Daytona Beach for spring break. And on the way back, we're going to say her average speed was 10 miles per hour less, and the drive back took her 5 hours longer. So it took her longer to come back. That's important because she went a little bit slower. Maybe there was more traffic. We want to find Sally's average speed on the way to Daytona Beach. So in order to start solving this, I've got some of it set up for you, and then we're going to go through some of it together. We're going to let x represent her average speed going. So that is the speed that she travels. And then if that's her average speed on her way there, x minus 10 would be her average speed for the return. So we know her speed or rate for both of those. And this little table is just something you can use to help you organize information in these. Some of you guys will find they're really useful. Some of you guys won't want to use them. Doesn't matter to me. I just find sometimes it's helpful to have. So if you think about it, her distance going is 1,500 miles. Well, her distance returning is the same, right? It's not the distance that's changing in these. What's different in these is the rate. Her rate or speed going is x. Her rate returning is x plus 10, right? Because she went, x minus 10, because she went 10 miles slower. We could do this with this being x plus 10 and that being x, but we're not going to confuse those right now. We're just going to leave x as her speed on the way there, x minus 10 as her speed on the way back. Then her time equals her distance divided by her rate. So her time going would be 1,500 divided by x. And then her time returning is 1,500 divided by x minus 10. So once we know what x is, we can figure those out. So now what we want to do, we know that going was the shorter time it took her, returning was the longer time. So because returning was her longer time, we know the difference between those two times has to equal 5, right? Because it took her 5 hours longer to drive back. So since it took her 5 hours longer to drive back, we know that this one, the longer time, is equal to the shorter time plus 5, right? Or her returning trip was 5 hours more than her going trip. So the longer one is the shorter one plus 5. So the other way to think about that, I'll just write that up here. Return trip equals the going trip plus 5 more hours. Okay, so what we can think about then, If we write it in words first, that's really a good strategy when you're doing a story problem. Then we can look at the expressions from up above. So our longer time, remember our longer time is right here in our table, so I'm going to replace that one with that, and our shorter time is right here in our table. So I can just take this and I can rewrite it as 1500 over x minus 10 equals 1500 over x plus 5. Now, this is a rational expression, and I can use my strategies for solving equations to solve that one. So let's take a look at what that's going to look like. Now we got to do the math. Let me just focus this real quick, and then we'll continue. Yeah, there it goes. Okay, so we're thinking about least common denominator. We have one denominator here, we have one denominator here, we have none here. So our least common denominator, nothing we can factor, nothing to do anything fancy with, so it's just going to be x minus 10 times 10. Remember, when we're solving, we multiply through everything by the LCD. So we get x minus 10 times x times 1500 over x minus 10 equals x minus 10 times x times 1500 over x plus x minus 10 times x times 5. So again, we're just taking this least common denominator, and when we solve, we multiply every piece of our original problem by our least common denominator, because what we want to do is we want to cancel denominators. So this and this will cancel, this x and that x will cancel, and I'm left with x times 1500 or 1500x equals 1500 times x minus 10 plus 5 times x minus 10. So this is a equation then that I can solve using strategies that we've learned in the past. So I'm just gonna chug through this. 5x minus 15,000 plus 5x squared minus 50x. So if I look at that, I can see it's going to be quadratic, so I want to try and move everything to one side and get rid of some of this stuff. So if I subtract this 1500x, I can subtract that there as well. That simplifies things a little bit for me. If I look over here now, I have a 5x squared. Those two just cancel, right? So I get a 5x squared. What else do I have? I have a minus 50x, and I have a minus 15,000. Now at first I might look at that and think, okay, that looks really complicated. I want to use the quadratic formula. I'm going to divide everything by 5, because that's just going to simplify it a little bit for me. That'll leave me with x squared minus 10x minus 3,000. So then from there, again, you might think about the quadratic formula there, but you also might notice that these are pretty easy round numbers. 5 times 6 is 30, and 6 minus 5 is 10. So if I think about it that way, I can pretty quickly see that my two factors are going to be x plus 50 and x minus 60. Again, just ignoring some of those zeros and thinking about the problem that way. So because now I'd have 50x and negative 60x, which gives me back negative 10, and I'd have negative 3,000, which gives me that. So then I set both those equal to 0, so x plus 50 equals 0, or x minus 60 equals 0. So x equals negative 50 or x equals 60. Well, negative 50 doesn't make any sense as the speed of a car, so we ignore this one. It's what we call an extraneous solution, and we just go with 60. So x equals 60, which means, what was our original question? Her average speed on her way to Daytona Beach. So if we go back up here, x is 60, that's this speed. Oh, that already gave us her speed going to Daytona Beach. So her speed to Daytona Beach is 60 miles per hour. And then we could easily find her returning speed also because we know to just, subtract 10 from that. But her speed going to Daytona Beach is 60 miles per hour. Moving along, we can look at work problems as well. So work problems are, actually before we do work problems, let's do this example 3. So just skip a page in your packet. We'll do the distance problems together and then the work problems together. So we've got walking speed. Marcy can walk 8 miles in the same time as Frank walks 6 miles. Marcy walks 1 mile per hour faster than Frank. How fast does each person walk? So again, remember, we're going to use that distance, rate, and time idea. So if you want to use this table, you can put that up there. You also, if you want somewhere to write time equals distance over rate, that's the formula we're going to use again and again as we do this. So what we've got, Marcy can walk, we need a row for Marcy and a row for Frank, right? Because we've got Marcy walking and Frank walking. Marcy walks 8 miles, so her distance is 8. In the same time as Frank walks 6 miles, so his distance is 6. So we know x is Frank's speed, so x goes here. Marcy's speed is x plus 1. Now, we don't know, what we want to think about here is what we're looking for. How fast does each person walk? And the other key to this one is that Marcy's 8 miles was in the same time, pretend like that's a highlighter, as Frank's 6 miles. So what we know is that Marcy's time equals Frank's time for this 8 and 6 miles. So Marcy's time is d over r, 8 over x plus 1. Frank's time is 6 over x. And those two things have to be equal because Marcy's time has to equal Frank's time. So Marcy's time was 8 over x plus 1. That has to equal Frank's time of 6 over x. So now we look at this equation, and we solve a rational equation. Our LCD is x plus 1 times x. So we multiply this by x plus 1 times x. We multiply this side by x plus 1 times x. We cancel out our common factors, so that and that go away, and that x go away. My fractions are gone. That's good. That's what I want. So I get 8x equals 6 times x plus 1. Well, let's distribute. 8x equals 6x plus 6 times 1 is 6. So subtract 6x on both sides. 2x equals 6. We'll have 2x equals 6, and we divide by 2. X is equal to 3. So if x equals 3, remember x is Frank's speed. So Frank walks 3 miles per hour. Marcy then, our m, well, it's whatever our x was, plus 1. So 3 plus 1 equals 4. So Marcy walks 4 miles per hour. And if you think about it, just to double check, if Frank was walking 3 miles per hour and he was going 6 miles, 6 divided by 3 would be 2. And if Marcy's walking 8 miles and she's walking 4 miles per hour, 8 divided by 4 is also 2. So it checks out. So we're good. And we can go on. Let's look at some work problems. Okay, so now let's go back to the second page of your packet and look at some work problems. So the big idea behind work problems is you have 2 or more people working on something. They each work at a different speed, and you want to know how long it's going to take to complete some kind of task. So the formulas, the algebraic models involve rational equations because work equals rate times time. So that leaves us with lots of fractions we end up with, and fractions are where we get rational expressions. So here's the 3 formulas, W equals RT, and then these are just 2 different variations of that. And we're going to use these as we go through the problem. So we assume that work's done at a constant rate. So if a job takes X hours to complete, the rate is 1 over X of the job per hour, because it's one job in X hours. As I said, some work problems have multiple machines or people working together for the same amount of time. That's going to be important. Same amount of time, but different rates. And then what you want to remember is when you have multiple people doing it, we're going to add the rates or the amounts of work, and we're going to always end up with one whole job being done. So if you look at example 2, after a heavy snowfall, Brian can shovel all the driveway in 30 minutes. His younger brother Alan helps. It only takes 20 minutes. How long would it take Alan to do the job by himself? So one thing that we know about this, if we think about it, we know that when Brian and Alan work together, they can do one whole job in 20 minutes. Okay, so we're going to organize that information into this table. Brian can do one job in 30 minutes. We know that because it told us at the beginning Brian, all of the driveway in 30 minutes. So all of the driveway is one job, and it took him 30 minutes. So his rate is one job in 30 minutes. So the time that he's spending, since they're working together and taking 20 minutes, this time column is 20 minutes for both of them because they're doing one job in 20 minutes. The work then that they do is the rate times the time. So 20 times 1 over 30, and I'll just, if you don't believe me, 20 times 1 over 30 is 20 over 30, and that just reduces to 2/3. So that's where we get that Brian's rate is 2 over 3. Then we look at Alan. Alan, we don't know how fast he works. So what we're trying to figure out, that's exactly what we want to know actually, is what X is. So X is how long it takes Alan to do the job by himself. In 20 minutes, we know he does 20 times 1 over X of the job. Whoops, you can't see that, sorry. So this was Brian, this one's Alan. 20 times 1 over X gives us 20 over X. So Alan's doing 20 over X of the job. So in 20 minutes, Brian's doing 2/3 of the job, and Alan's doing 20 over X of the job. We got to try and figure out how much each one of them are doing. So what we know is that Brian's work together with Alan's work gives us one shoveled driveway. So Brian's work plus Alan's work is one shoveled driveway, or 2/3 plus 20 over X equals one shoveled driveway. Brian's work, Alan's work. So we go through the solving process. We find the LCD, which would just be 3 times X here, because those are our two denominators. So I do 3 times X times 2 over 3 plus 3 times X times 20 over X equals 3 times X times 1. Come up here to continue that. 3's cancel. 2x equals, x's cancel, and I get, whoops, equals plus. Where was I? X is canceled over there. So I just get 3 times 20, which is 60, equals 3x. I look at that. I've got x's over here and x's over here, so I subtract 2x, and I get 60 equals x. Well, that's convenient. 60 equals x. So I know Alan takes 60 minutes to complete the job alone. Okay, and we got that by setting up the equation and solving it, looking at rates and how they compare. So the one other problem that we'll start together is on the next page again, example 4. I'm going to start this one for you but not finish it, and then I'm going to encourage you guys to finish this one before you come to class next time, and then we can talk about it and see where your confusion is, because I'm sure there'll be some, and that's totally fine. So we've got Kayoshi can paint a certain fence in 3 hours by himself. If Red helps, the job takes 2 hours. How long would it take Red to paint the fence by himself? So when we look at this table, we'll fill that out in a second. Kayoshi's rate, we know he can do one job in 3 hours. So rate, remember, is job over hours. Red's rate, he can do one job in, we don't know how long. That's what we're looking for again, 1 over x. So if I set up this table with Kayoshi and Red, and I put rate, time, and work up here, we're going to use this fact that together it takes them 2 hours to help us figure this out. So Kayoshi's rate is one job in 3 hours. Got that right here. Red's rate is one job in x hours. Together, it takes them 2 hours. And work, again, is always rate times time. So I'm going to multiply 1/3 times 2 and get 2/3 there. That's how much of the job Kiyoshi's going to do. Red, 2 times 1 over x is 2 over x. So then when I set up my equation now, I have one job completed equals Kiyoshi's work. So look back at Kiyoshi's work plus Red's work. So you fill that in, find your least common denominator, solve it. When you're done, you'll want to write Red will take blank hours to paint the fence by himself. So look back at the last example, follow it through, and see if you can figure out how many hours it would take him by himself. We'll talk about that next time in class. Thanks for watching, and have a wonderful day.